Okay, so I'm going to get started. Today's announcements are the exam regrades. The due date for those is 10 a.m. Wednesday. So if you don't have your exam back yet, which is a surprisingly high number of people, make sure you either get it from me after lecture today, or after that I'm going to distribute them back out to the recitation TAs so you can pick them up Monday or Tuesday next week. And then as a reminder, the way to submit an exam regrade request is staple a sheet of paper on the front saying, please regrade problem such and such. I feel I deserve more points back because da-da-da-da-da. Definitely check it against the key first just to see whether, I guess, like, that could be used as an argument in your favor. Like, the key shows it this way, I showed it also this way. They took points off for no reason. Or, you know, there are sometimes multiple correct answers too, so just because your answer doesn't happen to match what's on the key, it may still be okay. But if you're not sure, run it by me or your TAs first. And then just get it to me in person or my mailbox by 10 a.m. end of lecture next Wednesday. Okay, aside from that, we do have quiz number 5 scheduled for next week in recitation. I know that's right on the heels of exam 2, but it's kind of a good way to sort of reinforce stuff that people had a hard time with on the exam a lot of the time. So expect to see questions similar to the material that a lot of people miss. So some mechanism stuff, probably some chirality stuff. Maybe a little bit from today's lecture because we are starting chapter 7 today, but sort of a mixture of all that stuff. Okay, and then finally chapter 6 saplings due 9 a.m. Monday, and I will open chapter 7 hopefully later today. Questions about any of that? Okay, cool. So let's get right into chapter 7. Okay. So I mentioned that 6 and 7 are both taking a step back a little bit from any new reactions and looking at geometry for a while. And that's kind of what we're going to be doing in this chapter as well. So what we're looking at here is cyclic compounds. Okay. So anything that has a single ring in it is monocyclic. So they can have other stuff in them too, but this is monocyclic, this is monocyclic, a 7-membered ring with some methyls sticking off it is monocyclic. So all of these, assuming that they just got the one ring and no pi bonds, they're all going to have 1 degree of unsaturation. So if they're cycloalkanes, in other words. And 1 degree of unsaturation, we know the formula for that is going to be 2 H's missing out of our standard 2n plus 2 formula, which gives us CnH2n, because we're missing a couple H's. Okay, so this is actually useful information because it turns out we can actually treat this as some multiple n of CH2 groups or methylene groups. So what we can actually do is take all of the simple cycloalkanes and look at, first of all, their heat of formation, which is just when you assemble it from the elements that it's made of, how much energy gets released. And then we can look at heat of formation divided by n. So we can look at energy or stability per CH2 group, in other words. So we can do this little table of like, here's N, here's the name of the compound, and here's the heat of formation divided by N in kcals per mole. Okay, so it's basically like on a per unit basis, like how much energy actually gets released when we form these things from the raw elements that they're made of. So we're going to look at this for 3, 4, 5, 6, 7, and 8. Okay, so this would be cyclopropane, cyclobutane, and so on. It follows exactly the same naming convention as the regular alkanes, just with cyclo at the front. So in other words, if you wanted to draw these, you have a 3-membered ring, a 4-membered ring, a 5-membered ring, and so on, a 6-membered ring, 7-membered ring, 8. Okay, so it turns out the energy to build these things follows kind of an interesting pattern. When you're looking at the 3-membered ring and the 4-membered ring, not only do you not get energy out when you form this thing from the elements, you actually have to put energy in to get them to stick together as a ring. So this thing, you're pushing it uphill energetically. It is not happy about being in a 3-membered ring. It's very high energy and unstable, or reasonably high energy. A little bit less so for a 4-membered ring. Cyclobutane has still got a positive heat of formation. Cyclopentane is actually much happier about existing. It's downhill energetically from its component pieces, negative 3.7. Cyclohexane is negative 4.95 per CH2. Cycloheptane is negative 4.0, and then cyclooctane is negative 3.7. So in other words, the smaller rings, 3 and 4, are quite strained and high energy, and then 5 onwards is all like reasonably comfortable and low energy, with a local minimum or an overall minimum around 6-membered rings. So cyclohexane is the stablest, most happy, low energy ring that you can have, in other words. Okay. So it turns out that this is actually the same energy per CH2 group as a regular linear alkane. So this thing can get into exactly the conformation that it's most comfortable in, the same as just some linear alkane that doesn't have to worry about really any sort of angle strain except for avoiding eclipsing interactions. Okay, so what we're actually going to spend most of this chapter on is cyclohexane, just because it shows up the most often, because it's the most sort of stable and easiest to form in a lot of reactions. Okay, so this chapter could just as well be called Let's Look at Cyclohexane a Whole Lot. So that's actually what I have the model kit for here today. Okay, so cyclohexane we're going to show as a hexagon here, a 6-membered ring. So this is sort of the top-down view of the ring from above. But it turns out that if you tip the ring and view it side on, it's not actually a flat hexagon. It's got a little bit something else going on. So if we do view from the side, so I'm going to draw something and then I'm going to explain like how to draw it yourself looking like decent. So you may want to leave this spot blank for just now. But it's actually got this sort of zigzaggy thing going on, sort of like a zigzag drawing of a linear alkane. It's just, it goes around in a circle while it's doing it. Okay, so that's this structure that I've got here. You'll see that out of the 6 carbons that make up the ring, 3 of them have bonds that are pointing downwards and touching the table, and 3 of them are sticking up a little bit more. So here, I can hold this up a bit better. It's a good background to hold this against. Okay, so it's sort of alternating like up-pointing carbons and down-pointing carbons as we go around the ring. Okay. So how to draw. So this is what's actually called chair cyclohexane. And I guess if you sort of pick it up and like tilt it a little bit, you could see like these 4 carbons as being like the seat of the chair, and this is the back, and this is like the footrest or something going down. So we're going to be looking at how to draw a chair cyclohexane. The easiest thing to remember is that this whole thing is made up of a bunch of sets of parallel lines. So like one part of the ring is parallel to the part that's on the opposite side of the ring. So these 2 lines are parallel, these 2 lines are parallel, these 2 lines are parallel, and then all of the bonds that are coming off the sides are either parallel straight up and down, so like the vertical ones here on top or here on the bottom, or they're sticking out sideways, which means that this part here is actually parallel to this part here and this part here. So these 2 in ring are parallel to the sideways bonds that are sticking out like at the opposite corners to them. Okay, so how do we draw this? What you want to do is first of all draw 2 tilting lines, and I'm going to slope these ones up and to the left to start out with. And so the top one you want to have a little further to the left than the bottom one. So you want tilting up and to the left and then offset a bit. And then what you want to do is you want to do a V downwards here and a V upwards here. So sort of a good way to tell that you're drawing this in about the right shape is these 2 points should be about the same level, and these 2 points should be about the same level. And that, yeah, that's pretty close. Okay. So you can either draw tilting up and to the left, or you can draw the opposite handedness of chair, tilting up and to the right, and then the bottom one would be offset to the right a little bit, and then you just draw the V's pointing the opposite direction. So like that. Okay. What's a really common mistake here is that people will draw something that looks kind of like a bow tie. That's actually really hard to tell what's going on geometrically if you draw it like this. So drawing it this way, where like the front line and the back line are mostly overlapping but a little offset, makes it actually a lot easier, not just for me to tell what you're trying to draw, but also for you to figure out answers to questions as well. Okay. So what we have should look kind of like that model where we have alternating up carbons and down carbons. So like this one, and this one are all up pointing, while this one, and this one are all down pointing carbons. Okay, so that's the chair itself. What we can also do is draw in the bonds for the stuff hanging off of those chairs. Any questions first before we get to that? Okay, cool. Okay, so let's see, I'm going to stick with up and to the right for this because that matches my notes. Okay, so each carbon around the ring is going to have 2 bonds coming off of it. The down carbons have bonds that are pointing straight down. And for the ones that are vertical, either straight up or straight down, the name that we use to describe those is axial. So the down pointing carbons, I have a line sticking straight down. That's my down axial. And they also, if you look at what's required for tetrahedral geometry, they have a bond that's sticking slightly up-ish, or like just above level, that's parallel to sort of a part of the ring that's around the ring, a couple bonds. So the ones that are not pointing straight down, the ones that are all sort of around the periphery of the ring here that are like close to the same level as the ring, those are called equatorial because they're sort of, if you imagine the ring as being like a globe, they're sort of around the equator of the ring. So the down carbons have bonds that are down axial and up equatorial. So we're going to show those as this one here is parallel to this one here and this one here. Meanwhile, the up equatorial one here, I'm going to draw on that with like maybe just a different style of line. I guess I don't have any colored chalk, but if I did, I'd make that a different color. So this one here should be parallel to this one here and this one here. And then this one back here is also slightly up. Maybe let's do that as, I don't know, something with like a circle on it. That one there should be parallel to this one there and this one there, more or less. Doesn't have to be flawless, but it does have to be at least close enough that I can tell what you're trying to draw it parallel to. Okay, so that's the down carbons. Meanwhile, the up carbons have bonds that are up axial. So let's draw those in. We got an up carbons, straight up, and straight up. And then again, to get tetrahedral geometry going on there, we got to have bonds that are also down equatorial. So those are the ones that are slightly below level. So this one here is going to be parallel to the stuff that I've already drawn in as like a darker bond here. So this is parallel to these two bonds of the ring, plus also this up equatorial one on the far end. Here, it's going to be parallel to the ones with the circles on it. And then coming off of here, it's going to be parallel to the ones with the tick marks along it. Okay, so just to redraw this a little bit tidier, we should have a total of 12 groups coming off of the ring, 3 up axial, 3 down axial, 3 up equatorial, and 3 down equatorial. Okay, so I went through that last one pretty fast, but that's kind of a good thing to practice, is just drawing the ring and then drawing in all 12 bonds off of it. Okay, so questions about that so far? Okay, cool. So that by itself is quite a fair bit of geometry and looking at how things are arranged in space. Turns out it gets more complicated because what I've drawn as the up carbons and the down carbons can actually interconvert if this thing does what's called a ring flip. And I'm not happy about the name that was chosen for this because ring flip makes it sound like you're just taking the whole chair and just like flipping it around. A better name for it might be like a ring flex or a ring twist or something, because what you're actually doing is, okay, so we've got this one here that I'm holding on to is an up pointing carbon, right? Because it's got an up axial coming off of it. You guys can see that okay? Okay, so what we're going to do is we're going to take one of the up carbons and we're going to bend it to downwards, and then we're going to take the opposite corner and we're going to bend it to upwards. So I'm sort of flexing this thing into a different conformation. So this is what it's doing. It's really like flipping back and forth between a couple conformations. I'm glad I haven't broken this. It's very forgiving. So it can do a ring flip and flex into the other shape of chair. So I drew both a upper right corner chair here, might be a good way to call it, and an upper left corner chair here, and it's going to flip back and forth between both of those. Okay. So when that happens, of the ring carbons, the up carbons and the down carbons will swap places. But the groups that are attached to them, like up groups will still stay up and down groups will stay down, but anything axial converts to equatorial and vice versa. Okay, so I'm going to stick the foam balls on this thing to make this way easier to see what's going on. Just 1 second here. And I apologize if you're red-green colorblind. I'm going to try to do, I guess if I do yellow and green on the same ones, it might not matter. Okay, so right now what we got is yellow balls are down axial, red balls are up axial, oops, green balls are up equatorial, and purple balls are down equatorial. So you guys can all see that okay? Okay, cool. So what I'm going to do is when I do the ring flex or the ring flip, everything that's up is still going to stay up, but it's going to convert axial to equatorial or vice versa. So I'm going to grab this carbon here, and I'm just going to pull it downwards and pull this one upwards. So when I did that, all the red and green balls still stayed upwards, but I flipped which one's equatorial and which ones are axial. So now green is up axial and red is up equatorial. Let's go back and forth on that a few times. So right now, red and green are both up, but green's axial, red's equatorial. Now it's the other way around. Red's up axial. Now green's up axial. Now red's up axial. Okay, and I can do the same thing on the bottom here. Right now yellow is down axial, purple is down equatorial. Now it's the other way around. Purple's down axial, yellow is down equatorial. Go back a few times. So I'm interconverting yellow and purple, but they're both staying down the whole time. I'm just flipping which one is down axial and which one is down equatorial. Okay, so how to do this on paper. And actually, a lot of the time the way these problems are phrased is, here's the top-down view of a ring. So I'll give you just the hexagon-looking thing with some stuff hanging off of it, maybe indicated with bold and dashed bonds, so you know if it's coming up or down. And then I'll say, draw both chair conformations of this thing. And then you'll have to draw like both the different ring flip forms of it. So okay. So in the top-down view, anything bold is up, either up axial or up equatorial. Anything dashed is down, And then anything in chair that's either straight up or straight down is axial, and anything in chair that's like slightly up or slightly down is equatorial. Okay, so doing a ring flip is only going to change axial for equatorial and vice versa. It's not going to change which groups point up or down. Okay, and then finally, when we start looking at naming these things, we're actually going to use the same descriptors that we do for alkenes with cis and trans. But because there can be multiple different groups on the ring, we can use these to describe the whole molecule if there's only two groups. If they're on the same face of the ring, so example, both up, those are going to be cis. Two groups on the opposite face from each other are going to be trans to each other. Okay, so if we only have the two groups in the molecule, we can call the entire thing cis or trans. If we got like 3 or more groups, then we can only use this as like a pairwise descriptor, and we could say like these two groups are cis to each other, but the whole molecule isn't really anything. Okay, so let's walk through an example of how this might look. Okay, here's the top-down view. CH3, Cl, and then let's do OCH3. Okay, so let's draw both chair forms of this. Easiest way to start out with this is let's just arbitrarily choose to label one of the carbons in the top-down view to make it a little bit easier to keep track. I'm just going to throw a star on that carbon just as like a label. You can use like highlighters or whatever if you want. Okay, and I'm just going to arbitrarily pick one shape of chair to start out with. Let's do a chair that has a carbon in the top left corner. So in other words, the front and back bonds are tilting up and to the right, the way I've got it here. Okay. Again, completely arbitrarily, I'm just going to choose to have my starred carbon be over here. I kind of like having like my rightmost carbon here be the rightmost carbon there, but there's a bunch of correct options and ways to draw this. Okay, so given that my CH3 here is bold, that means it has to be sticking up in this chair form or in both chair forms. Off this particular carbon, does up mean that it's going to be up axial or up equatorial? Equatorial, right, because this is a down pointing carbon. It's going to have down axial and up equatorial. So that means I'm going to stick my CH3 group onto my up equatorial. Okay. So now I go the next carbon clockwise around the ring, has a Cl coming off of it, which is dashed, so that means it's got to be down. Is down here, does that mean down axial or down equatorial? Equatorial, yeah. So Cl coming off of there is going to have to be equatorial. And again, that's because this carbon is pointing slightly upwards, so its axial bond is also upwards. So if I want chlorine to go down, it's got to be equatorial there. Okay, moving around the ring, the next carbon has nothing going on there, so let's skip along one more around the ring to where we have an OCH3 up. So I go 2 around the ring. OCH3 is bold, which means up. Is up here axial or equatorial? Axial, yep. So again, this is an up pointing carbon, which means it has up axial, which means we show the bond sticking straight up that way. Okay, cool. So that's one chair form for this molecule. Questions about that one? Okay, yeah.
For that one, is it, I guess, it's hard to phrase, is it with the plane, so that's why you don't need dash and bold in the chair?
Good question. Yeah, so technically, I guess, like, it's kind of like I'm taking this hexagon that I'm showing you the top of when I drew this thing here, and I'm like rotating it so you're viewing it like almost edge on. So technically, like, yeah, if you wanted to get like really systematic about it, like you could show this entire part of the ring like receding away from you and this part coming towards you. Traditionally, you don't show any bold and dashed bonds on the chair because it's kind of implied by the perspective that you're using to draw it. So everything, all the lines that you draw on the chair should just be regular lines, and stereochemical information is sort of just implied by this style of drawing, I guess. Yeah, good question. Hi.
Could you have chosen to draw the cyclohexane in the opposite direction?
Yep, you absolutely could. So I'm going to do that one next. Yep. Okay. Any other questions about this chair form before I draw the other, though? Okay, cool. Let's move on to the other one. So, all right. So the way to tell that you're drawing the other option for the chair flip form is, in this particular case, the starred carbon that I chose to show, I happen to end up making a downwards pointing carbon, right? So after the chair flip, that means that I'm going to have to show it as an upwards pointing carbon. So assuming I want to keep it as like my rightmost carbon of the ring, which you have other options there, which I'll go through in just a second here. Easiest way to show this, if you're comfortable drawing both types of chair, is just have this one, just show like the opposite type of chair where the front and back bonds are now tilting down and to the left, which means that your top carbon, your furthest right carbon in the ring, your rightmost carbon, is going to be pointing up now instead of down. Okay. So again, we can go around the ring. CH3 is bold, therefore coming up off the starred carbon. Is that going to be axial or equatorial here? Axial, yep. And I can also check that's true because when I do the ring flip, I should be converting everything that's equatorial here to axial over here. Next carbon around the ring, I got Cl dashed. It should be pointing down. Axial or equatorial? Axial, nice. Oh, Cl down. And then I skip a carbon, and then I get over to here. OCH3 is bold, should be pointing up. Is that axial or equatorial? Equatorial, nice. Yeah. Okay, cool. So just to double check, CH3 stays up the whole time. It's up here, it's up here. Chlorine stays down the whole time. And OCH3 stays up the whole time. And all I'm doing is toggling axial versus equatorial on the two forms. Okay, so questions about that? Uh-huh.
So would we want to work towards doing this backwards also?
Yeah, so working backwards, assuming that I just gave you a chair form. If I look at this thing, I'm like, okay, well, it's cyclohexane. And I can pretty much use the same trick of just pick a carbon and star it if you want to keep track of it a little easier. So I've got CH3 pointing up. That means bold CH3 here. Next carbon around, I've got chlorine down, or dashed. Skip a carbon, and then I move around to here, and OCH3 is up. So I should have OCH3 up there, if that makes sense. Yeah, so it's actually quite a bit easier to move from the chair back to the top-down view because you don't have to get your bond angles exactly right. You can just sort of use bold and dash to show what the stereochem is going on there. Okay, good question. Other questions about this? Yeah?
Couldn't we just redraw that top structure as that one?
As this one?
That makes sense.
Oh, yeah. So I guess like if I gave you a test question that's just like, here's this guy by itself, like just draw the top-down view, then that would be fair game as well. So, okay. So one other thing that's worth pointing out about this is, so the last kind of note that I wrote up here for the rules is cis and trans. So anything that's on the same face of the ring is going to be cis to each other. So in other words, this OCH3 and this CH3, they're both bold, which means they're on the same face of the ring. So those are cis to each other. Chlorine is on the opposite side of the ring from CH3. So those are trans to each other. And then OCH3 and Cl are also trans to each other. Okay. So again, with 3 groups here, we don't really have a single cis-trans descriptor for the entire molecule. It's basically just like you got to go through a little piece at a time. Okay, so one last thing to point out about drawing chair forms is that this is probably the easiest way to see it. You straight up like flex the ring into the opposite form and you keep everything laid out the same. But it does require you to be able to draw both handednesses or both shapes of chair, either top left carbon or top right carbon types. If you can only draw one shape of chair, which is surprisingly common for a lot of people, here's how you're still going to be able to do a ring flip. Okay, so say I've drawn this one just fine, and I want to be able to ring flip that. What I'm going to do is draw the same shape of chair again. So again, I'm going to do. But I know that when I ring flip it, all of the ring carbons toggle from up pointing to down pointing and vice versa. So all I got to do is take this one, and now I'm assuming that I'm actually not just ring flipping it. Oh, damn. Yep. Yeah, some of the joints are getting a little brittle. I'm not just ring flipping it, but I'm also like rotating my view slightly at the same time. So I'm doing a flip plus 1/6 of a turn. Okay, so flip plus 1/6 of a turn. So I'm sort of spinning it around in plane at the same time that I'm doing the flex into the other shape. So my down pointing starred carbon now becomes an up pointing starred carbon. So it's the same operation I did over here, only I'm spinning it at the same time so I can avoid sort of giving away that I can't draw the other shape of chair in theory. Okay, so again, CH3 is still up. CH3 is up. Cl is down. Cl is down. Skip a carbon, and then OCH3 is up. OCH3 is up. So you should still get exactly the same results you did over here. OCH3 is up equatorial, same as over here. CH3 is up axial, same as over there. And Cl is down axial, same as over here. It's just you're showing it from a different perspective. So this is kind of another option that you have available to you if you need it. And you may see it that way in textbooks or if, I don't know, in like lab notes or whatever too. Okay. So questions about that one? Okay. So I think, yeah, I'm going to take just a couple minutes, clear the board off, and then we can spend like 5 minutes talking about relative stability of forms before I break off. Okay. So what we're going to look at just for a little bit here is what makes these molecules more stable or less stable. It turns out almost every group prefers being equatorial. So in other words, if we have two chair forms, one where we've got, say, chlorine axial, and the other where we got it equatorial, chlorine is going to prefer being equatorial. So this is more stable. And this is less stable. Okay, and the reason for that is it turns out when you're pointing up axial, it might not look like it on paper, but the chlorine here is actually crowding for space just a little bit with the two H's that are also pointing the same direction. So these two interactions here are costing us some stability. So these are called 1,3 diaxial interactions. The reason they're called 1,3 is if we assume this is the OH group and it's attached at what we're going to call carbon number 1, the H that's causing our problems is attached to carbon number 3 as we go around the ring. So carbon 1, carbon 3, 1, 3 both have axial groups, and these two things are kind of bumping up against each other. Okay, so every group has a slightly different cost for being axial, like an energy cost that it has to pay if it wants to go axial. In general, we're going to assume that for all groups, it's about the same cost, except for one particular group. So the one big exception is the T-butyl group, or the tert-butyl group. So if you remember, that looks like a carbon with 3 different methyls coming off of it. And it turns out this is such a huge, bulky group that this thing really, really, really does not want to be axial. Okay, so generally, if you've got 2 forms, it's just going to be majority rule. So more groups equatorial is more stable. So in other words, moving back over here to this example that I put up just a little bit ago, out of the 2 chair forms that I've drawn, this one has 2 groups equatorial and 1 group axial. So 2 ec, 1 ax. This one has 2 groups axial and 1 equatorial, so 1 ec, 2 axial. So this one here is going to be more stable. Generally, you just assume whichever has more equatorial groups is going to be more stable. The exception is if T-butyl is attached to the ring, we don't care what the other groups think because T-butyl just really does not want to be axial no matter what. Okay, questions about that? Okay, cool. Then I'm going to wrap it up here and have a good weekend.